Right, so carrying on with chapter 8. On page 8.7, last week I stopped here when I was talking about the second example on entropy. Now, something which I think you realized as well, I mean, I didn't specifically mention this, but in this example here, one thing you could do when you were thinking about, I mean, I did split this question into two parts. One was for the block and one was for the lake. Now, the block really was our system, so I could call this the system here, and the lake was a surrounding. So, the way that I could write this, I think we did actually find what is the change of entropy for the block, which in fact actually turns out to be negative. And we also found the change of entropy for the lake, which was positive. And then we said that you can add them up, and that would be the overall change of entropy of the universe, if you like. So, in other words, we could write that if I want to talk about the generation of entropy, so S-gen, it would be the total change of entropy. So the delta S total, if you do that, then you end up with how much generation of entropy you've had in the process. And that is really the change of entropy of the system plus the change of entropy for the surrounding and that has got to be equal or bigger than 0. The reason why I'm saying this and I'm revising these examples because actually it links back to what I'm going to do now on the next page. The fact that it shows that it's either 0 or bigger than 0, it just means that you can't destroy entropy, as we talked about in the past. So entropy is always increasing in the world, in the universe, and the only situation where you have actually the generation of entropy equal to 0 is when you have an isentropic process, which means there's not going to be any change of entropy as a result of that process. However, in reality, and whenever you have an irreversible process, you're going to have some sort of generation of entropy, which was the case actually in this example. And you saw that even though the change of entropy of your system was negative, which meant that your block actually gained more entropy, it gained actually more order. However, the overall change of entropy actually was a positive value, which meant that entropy overall increased. Something else to notice actually, because there was a very good question after the lecture on Monday about linking the entropy of the block to the level of order or disorder. I just want to clarify that, and bear in mind that when it comes to this block in this example, we know that when you start, you have certain amounts of entropy. When the block cools down, which is the case in this case, it cools down from 350 to 300 Kelvin. As a general rule, whenever a system or an object or whatever, it loses its temperature, then thinking about thinking about order increases. Why? Because higher temperature means higher movements of the molecules, therefore higher number of arrangements of the molecules, therefore higher entropy. When it reduces its temperature, think about the absolute 0. When I talk about that entropy would be actually equal to 0 because there's only one single arrangement of the molecules. So think about always the case that when the temperature of an object reduces, the level of order increases, therefore entropy actually reduces as well. And that's why actually in this case this was the case and where you end up with a negative change of entropy. But that comes at a price, because when you lose that temperature, that heat, the surrounding would gain that heat, and therefore the order of the surrounding will be reduced. So that is actually how these objects are balanced. Okay, so let's move on to page 8.8. I bet whenever you see this image, you panic. You say, oh God, now again all those equations. Well, we'll come back to this. Let's just think about, again, the generation of entropy and talk about what I just mentioned about those elements. So, I want to talk about the change of entropy in terms of ds, and I want to say that there are two components, if you like. One component is what we call the exchange of entropy, so that E stands for exchange, it's not exit or inlet or something, don't get confused with that. So this is the exchange of entropy, and the second term with the I, the subscript I, represents irreversibility. Some textbooks, actually, if you look at the textbook which is part of the which I've given you in the list of books of this lecture note and this course, they use actually different terminology, and so it's actually useful to know both of them. So sometimes instead of having SI or delta IS, you see S generation, which I just mentioned, and it makes sense. It's generation and production of entropy. In this course and in this chapter, we just use SI, as we'll see later on, or delta IS to represent the change of that S. And what is important is that the first term, which is the exchange of entropy, is nothing but that term which we've seen from the Clausius inequality. So remember last week, on Monday, I was talking about, we did a lot of derivation to show two corollaries of entropy, 4 and 5, and one of them was about this, that in entropy, the change of entropy could be related to delta Q divided by temperature. That term, which still is true, that applies to only the first component, which is the exchange of entropy. So it's the movement of entropy from one system to another, etc. That term does not take into account any production or generation of entropy, and that the second term there is the one that would take that into account. And of course, you can imagine that that term would be equal to 0, as you can see here, when you have a reversible or idealized reversible process, because if you assume that your process, your cycle is reversible, so it's isentropic, for example, it's completely idealized, there's not going to be any losses, etc. There's no change of entropy, as I just mentioned, and therefore the production of entropy will be 0. So the only thing which you have to bother or think about is actually this term, which then you can use this balance in order to relate entropy to heat and temperature, etc. So going back to S generation, or in this case, we can talk about, if you like, delta IS, really, or actually SI, let's say, to be consistent with the rest of this chapter. There are three possibilities. It could be bigger than 0, it could be equal to 0, or it could be less than 0. So, to summarize what I've been saying so far, if you have an irreversible which is the case in most of the real processes where you have irreversibility, the generation will be bigger than 0, because you're going to have some generation of entropy. It would be equal to 0 when there's no generation of entropy, and that only happens when you have a reversible, idealized reversible process. Do you know when you would have less than 0? Never. It's actually impossible. Because if you could have disruption of entropy, then obviously a lot of the systems, a lot of the theories that we've been introducing so far would have been wrong. Therefore, you could never have destruction of entropy. It's only either generation or the exchange of entropy from one form to another, from this system to that system. And I think the proof of that really is here. when and I think this is the link between what I've been saying here to the Clausius inequality. I'm not really too much bothered about this. What it does really, it just shows you that you can prove that if you look at just this bit, minus the integral of delta IS is equal or less than 0, which of course means that the integral for a cycle of delta IS is bigger or equal to 0, which just proves what we said here. That's just essentially what that is linked to, how that is linked to the Clausius inequality. Okay. And I think the rest here is exactly what I mentioned about the exchange and production. Again, please don't get confused with what I use as S generation. It's exactly the same thing as here, SI. That's the production, and that's the exchange. The reason why, you might ask then, why do we not just use S-gen in here, is because the I represents, because you only have that term non-zero when you have irreversible process, therefore you just use the subscript I just to indicate that it only exists if you have an irreversible process. This is just to clarify that. Okay. You always know that whenever we start with this simple configuration, you're about to derive some sort of transport equation or some sort of equation. And we've done that, I think this is probably the third time you've seen this figure. The terminology is exactly the same. Gamma represents the boundary of this three-dimensional, whatever you want to call that. That could be a, the way I see this is that this could be a balloon, for example. And here the omega represents the volume. N is the vector normal to the opening, and this is essentially an opening to this three-dimensional container or vessel. And what happens is that, assume that inside of this vessel you've got some sort of material or fluid, and in this case to be more accurate, and it's a very useful definition or a very simple configuration in order to derive unsteady conditions, unsteady equations. And what I mean by unsteady, you take the time into account. So, the first thing I'm going to start is this. You see V and N in bold. We've seen that before. Again, this just represents that you're interested in the vector form of the velocity, which is perpendicular to the opening in here. And of course, you're only interested in the perpendicular components of the velocity coming out of the three-dimensional geometry, because if you imagine this is your three-dimensional shape and you've got an opening which could have a sort of curvature in it, you're only interested in the components perpendicular to that opening. Therefore, use the velocity times n. But in terms of mathematics, this is really just the velocity. If I told you that you've got velocity times area, and dA represents that cross-sectional area here, you know that that's going to give you volumetric flow rate, because volumetric flow rate is velocity times area. If you multiply that by time, you can then calculate how much volumetric flow rate is getting out of this three-dimensional geometry or through this opening. Therefore, Vn dA dt would give you an elemental volume of material exiting through dA. If I multiply that now by density, let's just revise our fluid mechanics. Q UA, this is not heat, this is just volumetric flow rate. M dot is rho UA, right? And this is the same thing here. So this is rho UA multiplied by dt in order to give you the elemental mass exiting through dA. And if I now multiply that by S, that would give you the elemental entropy exiting the opening. You've seen that when we multiply this. If you replace S by E, for example, which we did, you would end up with elemental energy coming out of the opening. And here we're just doing that, the same thing, but replacing E with S, etc. By doing all those, The reason why I've shown those is because I want to arrive at this equation, which is the rate form of the energy entropy equation that actually has a very similar format to what we've seen before for the energy. The reason why I've been referring back to energy is because it's the same procedure. In fact, the left-hand side of these two equations are quite similar. You see here we've got the S. Here we had the internal energy, E. Here, instead of having E, you have S. So the left-hand side is quite similar. The right-hand side is quite different, actually, because this here is, again, the production or the generation of S. And this bit, as you can see from the format, Q divided by T, it's really the exchange, again, of entropy. Very similar, very consistent with what I mentioned about having two components, exchange and production. It's the same thing. When it comes to energy, if you remember, these represented the heat, and this represented the work. Now, tau is a surface tension, but you could express that in different form. But when it comes to derivation, and when it comes to the application of the energy equation to this geometry, you were interested in the surface tension, because the work in this case was the expansion of this, let's say, balloon. And therefore the surface tension was what you could define your work. But when it comes to turbine, compressor, things like that, obviously you're not interested in the surface tension. But this is just in terms of theory, this is how these two equations are related. So, in other words, the right-hand side of this equation, you had two forms of energy transfer, heat and work. Now, the question is, it seems when it comes to entropy, we still have something related to the heat, because you still can see the Q there. But then that term certainly doesn't have any resemblance to work. So it seems, even though so far we've been saying that these are quite similar, when it comes to entropy, what happened to the work? We don't seem to have any work term in the unsteady term for the entropy. And I'm going to explain why that's the case. If you look at the next page, the absence of the work term in the entropy is because work is an ordered form of energy. So far, we've always been saying that entropy is about disorder. So entropy is equivalent to disorder. So the fact that work is an ordered form of energy, it means that entropy actually doesn't take into account the work. Or so work doesn't contribute to the change of entropy. On the other hand, heat, which is a disordered form of energy, actually exists in entropy equation. Think about the block and the lake example which I gave you. That was about the heat exchange. I didn't talk about doing any shaft work or anything like that, because when it comes to doing some work, as you'll see later on, work necessarily doesn't lead to change of entropy or production of entropy. It's mainly the heat which is a big contributor to the production of entropy, and you can actually see that very clearly from the equation which we derived for entropy. So that is important to understand. Something else that I want to mention, and I think that is again the difference between these two, so it's quite important to notice, is that you always heard, and it's actually quite obvious, that we have something called conservation of energy. And the first law was actually based on conservation of energy. Do you think we have something called conservation of entropy? Do you think we could have something equivalent? Who says yes? Have you ever heard of conservation of entropy? No, because again, for the same reason as I mentioned, entropy continuously changes in the universe. If you see the whole universe as a control volume, then the entropy within that control volume actually is changing all the time. Whereas that's not the case with energy. We say that the level of energy in the universe actually doesn't change. It just changes from one form to another. But that's not the case in entropy. Therefore, the entropy is actually a non-conserved. Entropy is a non-conserved let's just call this parameter for now. As it's a quantity, it's a property, as we showed. So it's a non-conserved property. It only is conserved when you have an idealized reversible process. Why? Because the production of entropy is then zero. So let's be clear on that. What we know, if you're just saying that the conservation of energy is only when you have an idealized, cases and with no losses, that's not really useful. The conservation of energy applies to anything, but the conservation of entropy only applies when you have an idealized reversible cycle or process. Okay, enough of that. So we've touched, we have introduced and we talked about entropy so much. What I want to do now is start looking at the application of entropy to a number of systems, and open systems, in fact. So, going back to slightly simplified, or actually this is the steady form. The two equations you saw on the previous page, these are exactly the same. The only difference is that I got rid of dSCV by dt. I got rid of that, which was the unsteady bit, and the dECV divided by dt. So if you remove those two terms, you essentially end up with a steady version of those equations for the energy and entropy. Okay, so of course we are interested in open systems like a throttle and compressor and turbine. Therefore, we are interested in the rate form of these equations, and you can see Q dot, W dot, S dot, etc. But that doesn't necessarily mean that we are interested in the unsteady nature of them. We can assume, for simplification, we can just assume that you're interested in the steady type of systems. So no time, just to clarify things and to make things a bit more simple. The first example, or the first device I'm looking at, is a throttle, which is the same as a valve, or very similar to a valve in terms of physics and how entropy or energy changes across a valve. If you remember, I introduced a throttle or a valve as what we call isenthalpic device, which means enthalpy is the same across that device. Let's just see that, if that's the case here. So, entropy, we said that the exchange of entropy is defined as this term. But in reality, there's no heat flux in this case, and therefore, when it comes to the change of entropy, then that's slightly different, because you are saying that the only term which contributes to the change of entropy is now probably zero, because there's no heat exchange happening there. Let's see what that happens, what that does to the equations that we've had so far. As far as the energy equation is concerned, let's start with the energy equation. The right-hand side of the energy equation, both of these terms will be zero, as you can see. So Q dot and W dot S will be zero, as we know, for a valve or a throttle. So what you end up with is H2 equals H1. If you don't remember what this E superscript H is, go back to chapter 5. That's page 5.3. If you want to revise for yourself. But just to remind you, EH, so E is the energy essentially, but the superscript H comes as a result of entropy, and E plus PV, that's what EH really is. And if you want to relate that to entropy itself, as you know, E itself is U plus half V squared plus GZ plus PV now. So this is E. And I can combine U and PV, which is defined as H. This is exactly how H is defined, plus half V squared plus GZ. So this is what EH really is, in steps, if you like. In any case, because there's no kinetic energy or potential energy in this case, that's why when it comes to EH, the only term which is non-zero would be entropy. And then you're going to have H1 equals H2. What about the equation for entropy? Well, there's no heat transfer happening. There's no Q, therefore that exchange term is 0. What about the production? The production actually is not 0, and therefore the SI term is simplified to the fact that you're going to have some production, and it's going to be bigger than 0. So the production of S is going to be bigger than 0. And why do you think that's the case? Even though you don't have heat happening, why do you think, as a result of throttling the flow, or as a result of introducing a valve into your system, why do you think you would have production of entropy? Think about it from a physics point of view. So what happens to the flow? You're restricting the area. Yeah, exactly. So you would have turbulence, for example. Yeah? And that turbulence, or whatever that is, actually would introduce some losses, and that loss would manifest itself in production of entropy. Okay. Something about, before I move on to the next one, is about the degradation in the quality of energy. So, the fact that entropy goes up, the quality of energy actually goes down. And actually, when we do one example, if you have the time, you'll see exactly what I mean by the quality of energy. It's a lot easier to define the size or the quantity of energy, but when it comes to quality, it's very difficult. And the only way to comment or assess the quality of energy is by looking at the entropy. And I think I think this is actually really why entropy is so important. It comes into lots of different equations and problems. Let's look at a nozzle. A converging diverging nozzle has a lot of applications. That's the second example, actually the second device we're looking at. So point 1 and point 2 are just upstream and downstream of the neck or the narrowing of this nozzle. Starting with, again, the energy equation and the entropy equation, let's just see what happens. As far as the energy equation is concerned, again, you have no Q, you have no W. This time, because there's some form of, this time you can't ignore the change of velocity. Therefore, you've got to retain this term and this term on both sides. And your energy equation is reduced to that, to this equation. What about entropy? Well, no heat transfer happening, therefore there's no exchange of entropy. What about production? Do you think we're going to have production? No, and the reason for that is because, as you mentioned this time, we're not going to have actually losses, we're not going to have recirculation, we're not going to have turbulence, because it's a very smooth sort of narrowing of the fluid. So it's quite effective in terms of maintaining the momentum and minimizing the loss. And as a result of that, there's not going to be any production of entropy. What happens when there's no exchange and there's no production of entropy? You end up with a situation where literally entropy doesn't change from point 1 to point 2. And this is what we know as, I'll discuss exactly what, I have defined, like, for example, isobaric and entropic and everything else. We have something which essentially we know as isentropic or isentropic, and this is exactly that representation. So whenever you have a system where the entropy doesn't change in that system or that cycle, we have that. We say that this is an isentropic cycle, and that's the term we use for that. So, is there anything else I want to mention about this? Oh, yeah, something important about this aspect and the term isentropic is that when you have adiabatic situation, so there's no heat transfer happening, which is the case in the nozzle, and when you combine that with a reversible process, which means you're not going to have losses, which is the case again in the nozzle, of course you're going to end up with something called isentropic. However, and this is the point which I want to raise here, the opposite is not true. So that's not actually true. So if you have an isentropic process, that doesn't mean that is necessarily adiabatic and reversible. Why? Because you could have situations where you have some exchange of entropy and you have some production of entropy as well, but they have negative signs and negative magnitudes, therefore they cancel each other out. So you end up with an isentropic process, which means change of entropy is going to be 0, but you had some production of entropy and you had some exchange of entropy as well. Therefore, the opposite of that is not true. The third device is a turbine. That's a symbol, as you know by now. That's a symbol we use for a turbine. Assuming that there's not going to be any, that's a big assumption, but we have to make this assumption in order to make this work. We assume that there's not going to be no heat losses in a turbine. So Q is going to be equal to 0. We assume that there's not going to be any kinetic energy and potential energy changes. So all three will be 0. These two are common and it sort of makes sense, but the first one, which is the no heat losses, you might, and I think I have mentioned this as well, you might think that turbine certainly is a very hot component. Obviously it has to be quite hot. It's operating at high temperature. Therefore, how can you ignore the fact that there is some sort of heat loss there? If you have a perfect or perfectly insulated casing for a turbine, then you can assume that regardless of the temperature, you're not going to have any heat losses from the turbine itself. So the fact that a device or a system is operating at 500 Celsius, 600 Celsius, whatever, that doesn't mean that it doesn't have, it can't be adiabatic. It can, if you assume that you have perfect insulation. And in this case, actually, that's the assumption we're going to make. So, looking again at the energy equation and the entropy equation, the term Q, as I just mentioned, is going to be 0. But of course, what cannot be assumed to be 0 is Ws. Otherwise, what's the point of having a turbine? Therefore, looking at what other terms are non-zero, you end up with H2 minus H1 on the left-hand side, and on the right-hand side, you're going to have minus Ws. So your work essentially is equal to the change of enthalpy. What about entropy? In fact, because of the no heat loss assumption, you're not going to have any exchange of entropy, and you're not going to have any production of entropy in this case, despite having some work. Remember what I mentioned about the work and the heat and the difference they have on entropy? And I said work is an ordered form of energy, whereas heat is a disordered. If you have heat involved in a problem, you can't have isentropic. But if you have work, with some of the assumptions, you could actually have an isentropic process, which is actually the case in this example. So that means that a turbine is an isentropic device, and in fact, the same thing applies to a compressor. I haven't included compressor here, but compressor would be exactly the same. So the equations that you see here would apply exactly the same to a compressor. So let's just make this comment, same for a compressor. The next example or device is a heat exchanger. In fact, because I decided to skip heat exchangers from the very beginning, this is going to be optional, which essentially means you're not going to touch it. So I know that. So let's move on to the examples. This example, I think, is from a past paper, so it's quite important. It sort of shows a level of, the sort of questions that you would expect in the exam. And it shows something about the energy degradation, which I just mentioned 10 minutes ago. So let's see what we have here. We have a, let me just draw this because it might be easier. So we have a throttle, then we've got a turbine, and we assume that the inlet here, we have steam. As soon as you hear the term steam, you know that you're going to be dealing with the steam tables. And this is a pure substance. Steam at 60 bar, so P1 is 60 bar. Dry saturated, which means X is equal to 1. This is exactly how I want you to answer these questions in the exam. As soon as you have an information in the question, try to write down what that is, P1 in this case, X1. Draw a simple diagram. You can change that if you want, but draw something that makes sense in your mind. So it's fed into a turbine via a throttle valve. The steam leaves the turbine at 0.08 bar, and the turbine is isentropic. In the future, in the second or third year, you might have situations where you would do some calculations for turbine or compressor, and maybe you're going to have some losses, and you're going to account for some losses there. So it may not be isentropic, but in this course, whenever you have a turbine or a compressor, you should assume, even if it doesn't say that, you should assume that it's actually isentropic. Without that assumption, you can't actually carry on and do the calculations, because you would need a lot more information than just the pressure and the X and etc. So it's important to make that assumption. First of all, drive an equation for the turbine. You would do that naturally anyway. A, find out the amount of mass flow rate that you need to have going through the turbine in order to produce 10 megawatts of power. And then, in the second case, assume that you have now the throttle in place, and it's throttled to 40 bar before going to the turbine. So there are two examples. There are two cases. The case one is assume that this doesn't exist, and in case B, assume that you have these two components. Starting with our derivation, I have shown that this is the equation which applies to a turbine. Ws is equal to the change of enthalpy, depending on whether you're looking at the capital W or a small w. Of course, that makes a difference where m dot is, but m dot is very important because that is something which comes into our calculation. This is what you want to find. So it seems like you are after Ws dot, and you want, sorry, you've got W dot S because that's 10 megawatts, and you want to find that m dot. So we know this, and in order to find that, we need to find the enthalpy before and after the turbine. So you go to the steam tables. I'm not going to show where, because we've done so many examples, so I expect you to be able to find that anyway. At 60 bar, you want to find what is the saturation temperature. You may not use that now, but anyway. And the other thing that you're interested now is what is H. Do you know why I've set here page 7 or page 5? Because normally, if you are after something, there's only one page or one location that you can find it. Why do you have two options here? Just out of interest. Any idea? Without looking at the steam tables? It's only because here I had x equal to 1. And when x is equal to 1, think about that diagram. You are here. So page 5 gives you the multiphase region. Page 7 gives you the superheated steam. And in any case, because this is on the border, you can either find it from page 5 or page 7, depending on whether you want to approach that from the two-phase flow aspect or the superheated steam. So that is why you could either find the value, from page 5 or 7. Anyway, H1 is equal to Hg. Why? Because as I just mentioned, you are on this line, and whatever value here, that would be your Hg or Sg, etc. That there, okay? So, you found H1, that was easy. In order to find H2, you've got to rely on that big assumption which we made, which is the most important assumption, which is that the turbine is an isentropic device. So, here, this is the configuration for us, inlet and outlet. What you know, and I told you before, when you have state 1 and state 2, position 1, position 2, etc., you always have to look for something which would link the two positions. The thing which would link these two in here is the fact that S1 is equal to S2. Which means, if you find what S1 is, then you can find S2, and from S2 you can find what H2 is. That's the sort of the bridge, if you like, between point 1 and point 2. So, on page 7 or 5, you find Hg and Sg very easily. And the fact that now you know the value of S1, that means that that's also the same as S2. And how are you going to use that value? Well, you've got to use the other information that you have from your question, and that was the pressure at the outlet. The pressure at the outlet allowed you to find what is Sg and Sf at that point as well, which is given on page 3. By knowing these values, then you can go to the equation that we had for x. Remember, the dryness fraction could be found by either looking at H or S, or actually even V, which was the specific volume. So x can even be found, just as a reminder, V minus Vf, Vg minus Vf. Depending on what you have in your question and what is given to you. Here, because I now know what S2 is, that allows me to, and actually very easily I can find SF and SG. I just found those values from the steam tables. By knowing those values, allows me to find X, and if you know the value of X, you can reverse the process and find out what is actually H2. That's what you've done here. I've just rearranged that equation, and I've rearranged it in order to have H2, and you find what H2 is by this very simple equation. And all you need to do now is just insert those values into your equation and find out what is the mass flow rate. So what we did, for the two pressures that we had before and after, we found what is SG and SF and HF and HG, and from those, it allowed you to find what is the mass flow rate, what is the enthalpy in both cases, and therefore as a result you can find what the mass flow rate is. Now, I have to go through this quickly. The fact that now we have a throttle, it sort of makes the equations slightly complicated, but still it's not that difficult. It's the same principle. The configuration now, as you can expect, now looks like this. So, across here, S1 is equal to S2. And the only thing to realize is that across here, H1 is equal to H2, if you like. So, when I was talking about the bridge, or that information which would transfer from point 1 to point 2, when you have a turbine, that was the entropy, which was the same, and you could use that information. For the throttle is the enthalpy, which would be the same before and after. And using that information, that allows you to work out exactly what you want, which is the final H2 at this point. Okay, so very similarly, you look at the pressure that is given to you. You look at the steam tables. In this case, it's page 4. You find what is Hg, and of course, you know that would be your your H1. And now, this time, I'm going to use this H balance because I've got the value of F and Hg and H1. That allows me to find out what is my X. It's actually 0.99, which means this time it's not 100% dry saturated. It's just slightly lower than that. It's 99% dry. Doesn't really matter what that value is. The reason why you care about that is because that allows you to apply to this equation and find out what is your value of entropy. And that's exactly what we've done here. That value shows what is the entropy which is just going into the turbine. And now you know that in order to move from before the turbine to the after of the turbine, upstream and downstream, you just have to link the entropy. And therefore S1 is equal to S2. S1 is equal to S2 across the turbine. This is just a repetition of what we've done here, but with slightly different values, because your X now has changed. Once you go through those equations, what you end up with is the value of m dot as 11.2 kilogram per second. Now, of course, I'm very interested, you must be interested in the way that this is calculated. This is extremely important. As far as the entropy degradation is concerned, or the quality, the energy degradation is concerned, look at these two. You introduced a valve, a throttle. What happened is that to maintain the same amount of power, or to produce the same amount of power, you had to increase the mass flow rate. What does that imply? That implies that, of course, by providing higher mass flow rate, that means you need to provide more energy to your turbine. And that's not good. So, by introducing this throttle in your system, you had to increase the mass flow rate to maintain the same amount of power. Therefore, the energy degradation which I talked about, in this case, manifests itself as the increase of the mass flow rate, or the amount of energy that you provide to the system. Okay? And this is exactly what we mean by energy degradation. So, we're going to stop here, and on Monday, I'm going to carry on with 2 more examples, and we'll take it from there. Are there any questions before we stop? Okay?